Hi, good morning, everyone. We're about to get started. If you could all take a seat, we're going to kick things off with a video, and then we'll do a few words of welcome.
When we look at the world around us, we typically measure it in inches and centimeters, miles and kilometers. But in the field of nanotechnology, we work in nanometers. That's 1/1000th of a meter. If you take a dime and slice it on edge 1,000 times, take one of those pieces and slice it another 1,000 times, you now have one piece that's 1 nanometer thick. When you start looking at the world on a nano level, everything changes. At the IIN, we're not just imagining the future, we're building it 1 nanometer at a time. The IIN is the International Institute for Nanotechnology and is one of the largest, if not the largest, nanotech operation in the world that focuses on the pure aspects of nanoscience and technology.
Nanomaterials are really the building blocks of our world. Atoms and molecules assemble to form nanostructures, which ultimately make up the properties of the materials that we live with and that we work with.
Whether it's in clean energy, the development of medicines, the development of materials for food and water safety, the way we create major solutions to some of the biggest problems in the world is through nanotechnology. The problems that we're going after, they're too big to go after alone. They require lots of different folks coming together from different disciplines. That's what the IIN does and does really well.
The opportunities to collaborate within the IIN is really the secret sauce. The science at IIN is like none other in the world. But what makes the IIN stand out is this amazing network of scientists and forward thinkers.
We're looking for people that define thought. The IIN's become a major hub of discoveries and inventions that are impacting people all over the world.
The IIN is one of the world's globally leading institutes in energy and sustainability. Researchers at IIN have developed the capability to produce what are known as mega libraries. These are millions of candidate materials that can be efficiently screened for sustainability and energy applications.
I work in a class of materials called metal organic framework. Another way of thinking about these materials as smart programmable sponges, we have the ability now to put our MOFs on the textile of uniforms to capture toxic chemicals and detoxify them instantaneously.
What we're seeing as a whole with nanotechnology and medicine is that nanotechnologies are really on the cutting edge of advancing care for our patients.
Spherical nucleic acids are kind of a hallmark invention of the IIN. Normal DNA will not enter cells freely. Spherical nucleic acids do. That allows you to move large therapeutic payloads into cells that allow you to treat a lot of very debilitating diseases.
IIN is working on a very exciting field of rational vaccinology.
The concept behind rational vaccinology is that you can take nanostructures and begin to put those components in different forms, and there will be a form that will give you much greater efficacy than all others.
In cancer therapies, it allows for us to develop a vaccine against a patient's cancer that's specifically targeted for that patient.
That is going to be a really, really powerful avenue of drug development, and one that I think is going to change medicine forever.
So you've got a structurally well-defined lead compound, and we can then systematically look at structure-function relationships.
It's on the way.
We have to make sure that we're not only doing cutting-edge research, but that we're beginning to train new generations of people that are going to have the skill set required to do this at the highest level and the passion to do this at our level.
I'm investigating developing a protein-based cancer vaccine. Being at the IIN, this is really the hub of where nanotechnology is. We have access to so many great faculty that are leaders in their own field. We're encouraged to come up with these new ideas that can really have a paradigm shift.
As scientists, being at the edge of science is what makes you get up every morning.
The future of the IIN is really quite bright. Everybody at the IIN is driven by the idea that nanoscience can make the world better. We've created something that really is the envy of the world. We knew it was going to be big. We just didn't know it was going to be this big.
Okay, great. We always like to use that video just to give you a little feel for what the IIN's all about. And this is now, I think, our 23rd or 24th year of doing this. We now call it the 2025 IIN Rosemary Schnell Symposium, and that's in honor of Rosemary, who is one of the biggest fans of nanotechnology here at Northwestern and around the world. And it kind of gives you a feel for, I think, what this field does. It elicits incredible excitement among all the scientists, of course, to participate and contribute. It draws people in. You look in that video. I've got handsome Ted Sargent up there. Omar, pretty handsome, in the back. Attracted from really all over the world to come to Northwestern, bring their talents, and raise their game and raise our game. And I don't think anything in the history of Northwestern has done better at that. You look at the people that have moved here: John Rogers, Shana Kelly, Terry Odom, Sam Stoop. And it's created just an incredibly vibrant environment, and one that really excites the students and everybody who's involved in the research and makes us a lot better. Rosemary came to one of these events and she heard Mark Ratner. Mark Ratner was actually my partner in building the IIN in the early days, and he used to give a Nano 101 talk. Rosemary's not a scientist. She was a school teacher, and a lot of fun, actually, too. And she used to come to these events and never missed one. And at the end decided that she wanted to give everything she had to nanotechnology. So she bequeathed her entire estate, or a large fraction of it, to the IIN. And we've used that to make this symposium free to everybody, along with some contributions from other sponsors as well. It's kind of our give back to the community. It was very important to her, very important to us. And also to begin to recognize a lot of students for some of the great things that they're doing. So there are different awards, and that ultimately enriches the whole place as well. So we're incredibly grateful to her long friendship and ultimately to her real commitment to nanotechnology and helping us take it to the next level. We've got a big event planned today, and what I love about this, you look at I think many of you have been here many times throughout the years. This just continues to attract the best and the brightest from all over the world. You look at the picture from all the different symposia, it's remarkable. An enormous number of Nobel Prize winners, leaders from all parts of the world, and no exception today. You're going to hear from Nicholas Pepys, who's the Kabiller Prize winner this year, from the University of Texas at Austin, from Nathan Gianeski, from Northwestern. He's won also one of the Kabiller Prize, the Young Investigator Award. And then Mike Mitchell from UPenn, who won the Rising Star Award. Really fantastic people, all in the kind of the bio-nano space. But we look at nanotechnology broadly defined, and you're going to hear from Sir Richard Friend and Tanya Weil and Michael Graetzel, incredible leaders in their own rights in their own fields, and give you a really broad perspective on really some of the exciting technologies and discoveries coming down the pike. We have an incredible group of supporters. I mean, I always say that, it's NU, it's not Northwestern University, it's Nano University. Some of the PR people argue with me on that, but that's what I'm going with. And we've gotten a lot of the top folks at Northwestern to really understand the importance of this to Northwestern, the importance of this to the world. And these are the many people that have supported the Institute over the years and really give us all the resources we need to do this at the highest level, and we're incredibly grateful for that. We also have, every year, fantastic sponsors. And this year we've got Joel, represented by Brandon Brandt, Marshall Gerstein, who's been with us for a long time, Pam Cox, she actually handles all of our patent estates, work with her on a regular basis, absolutely fantastic team of IP lawyers. Hitachi, Bob Basseri, Joel and Hitachi have a lot of equipment here, and as I think many of you know, technology, equipment, state-of-the-art capabilities really drive science. So they're big players in this field and at Northwestern as well. We've got GSK and Glenn Research and American Elements, who couldn't send representatives this year, but did provide significant contribution that allows us, as I said, to make this free to the general public and the science community. But I guess this is so important because these people, somebody said, well, this is such a well-run event, everything goes well, and they said, Chad, you're really good at this. I do none of this. I have an incredible team, IIN staff led by Sarah Petrosko here. You're going to see these people. Please thank them when you do because they make everything run flawlessly. They hopefully make me look good. I'm incredibly indebted to them, and we are all as well at Northwestern because this has become a real gem for the institution. I'm going to turn things over to Sarah, who's the Associate Director of the Institute, to give you a little feel for some of the things that happened this year. Thank you.
Hi, everyone. Thank you, Chad, for the introduction. So before we get started today with the program, I just wanted to say a few words about ways in which the IIN is fulfilling its mission. So our mission, very broadly, is just to advance and enhance nanoscience and nanotechnology at Northwestern and globally, and we do that through efforts in research, education, translation, and also infrastructure development. So everything we do at the IIN, first and foremost, is about the top-notch, rigorous science that we all do. Nanoscience and nanotechnology is a very interdisciplinary field, so we have efforts spanning all these areas, from medicine to clean energy to security. And one thing that the IIN has done really well over the last 25 years is really amass an enormous amount of resources to support these efforts. We've been able to establish dozens of research centers that bring together collaborators from all across the university, as well as 60 other countries around the world to basically engage in this cutting-edge science that leads to emerging fields. And we also support science at Northwestern by doing things like recruiting the best and brightest faculty members that define departments, like Chad mentioned. And we also do a lot of seed funding to really get these emerging areas off the ground to where they can really go after some of bigger funding opportunities. So I just wanted to mention that our research impact doesn't end in the lab. The IIN, we are really passionate about creating a culture where everyone is passionate about bringing things out of the lab into the real world where they can really make a difference. And the IIN affiliated faculty over the years, through support from the university and offices like INVO, have started over 40 startup companies that have employed thousands of people in the Chicagoland area and elsewhere, that have generated over 2,000 products, and that have generated really enormous amount of IP. So you saw in the video that the number is over 3,200 patents and applications that our IIN affiliated faculty have been involved in. So who are these people that make all this research impact possible? So you saw in the video that it was over 220 is the number of people that we count as affiliated faculty. These come from all across Northwestern, from over 35 departments across 4 schools. It's the breadth of interdisciplinary people we have engaged is really remarkable, and every year we invite more people into our enterprise. And those are the people you see on the screen here. And they're just a good representation of what I just said, the interdisciplinary effort that we have. Anyone from chemistry to medicine to engineering, we try to pull them all in and get them engaged in our effort. In terms of postdocs, so all these affiliated faculties have full labs that encompass thousands of postdocs and also thousands of grad students. The IIN has been lucky enough through our various fellowship programs to support over 60 of these through fellowship support, which includes money for stipends, research supplies, extra travel to enhance their experience. And these 6 that you see on the screen today are the ones we've honored just in the last year or so. And then I was mentioning graduate students. So Chad was talking about the Ryan family being huge supporters of Nano. So in 2007, they gave a generous gift that established the Ryan Fellowship Program. So this is for outstanding nanoscience and nanotechnology graduate students at Northwestern. We've been able to support over 300 since 2007 with this fellowship. And we welcomed those you see on the screen in the last cycle, which includes incoming freshmen to Northwestern, as well as honoring current students who have just done an outstanding job. And then finally, I just wanted to say a few words about our very youngest nanoscientists, our undergrads, and even our middle schoolers. So we're really excited to announce a new NSF REU site that's going to be starting next summer at the IIN. And this really continues a long tradition of REU programs administered by the IIN that have encompassed over 400 undergraduates from across the country since 2002. We're really excited to get that program back and up and running. For the NU freshmen, we just started a few years ago the NU Nanoscientist program, and this is in collaboration with the Department of Chemistry, NU Arch Scholars, and then also through support from Materials Science. And this is to give Northwestern freshmen the possibility of 4 full years of, should they choose, of research in the lab to really prepare them for the next step of their careers and to try to keep them engaged in STEM majors. And this program has the possibility of supporting up to 15 Northwestern freshmen a year. And so we're really excited about it because multiple of the students that have been a part of it have actually already published papers with their mentors. So it's turning out to be a big success. In terms of, like I said, the very, very youngest nanoscientists, we do the All Scout Nano Day every year. There have been over 20 that we've hosted here. And Mike Kleppinger is in the audience, and he was the person that reached out to us, as the story goes, and thought this would be a really great idea to get middle school kids interested in what we're doing here at Northwestern. So he's been a partner over the last 2 decades, getting that program off the ground and continuing to grow it. And then the final thing I'll say is just about the IIN's efforts in communications. So I think we've all seen in the last year just how important communication is, and we as scientists need to be able to make what we do and its impact and its importance understandable to the general public, as well as even just people outside of our field. And so our part of that is the Nanoscape podcast. And so it's in its 2nd season. Many of you have probably listened to episodes. If you haven't, you should. They're really good. It recently won the Office for Research Innovation Award. So if you tune in, you can listen to Seth Zimmerman, our IIN Associate Director of Marketing and Communications, and science communicator Aaron Spain interview some of the top folks in nano at Northwestern. We've had people like Shana Kelly, Omar Farha, Rule Templar. It's really great because they don't just talk about the science, it also gets very personal. You hear a little bit about the scientists behind the research. And if you may have seen last week, we had Nicholas Pepis, one of our Kabiller Prize winners. And then we have a future episode planned with Tanya Weil, and you'll hear from her later today. So another of our passions at the IIN is just to create spaces like these where people can come together and talk about their research and celebrate it and talk about where we're going as a field. And so now I'm going to pass it over to Mercouri Kanatzidis, who is a professor at Northwestern, and he's going to introduce our first speaker. So thanks so much, everyone.
Good morning, everyone. It is my great pleasure and honor to introduce to you Professor Michael Graetzel, a visionary scientist whose pioneering work has fundamentally reshaped how we think about energy, materials, and the interface between light and matter. Professor Graetzel is internationally renowned for his trailblazing research in photonics, material science, and renewable energy. He currently serves as professor at the École Polytechnique Fédérale de Lausanne, or EPFL, in Switzerland, where he leads the Laboratory of Photonics and Interfaces. Perhaps he is most widely known as the father of artificial photosynthesis. Professor Graetzel co-invented the dye-sensitized solar cell, or the Graetzel cell, in 1988, a landmark innovation that mimics the natural process of photosynthesis and converts light into electricity. This technology laid the foundation for a new generation of affordable and flexible solar energy solutions, helping to usher in the modern era of renewable energy research. Over his distinguished career, Professor Graetzel has published more than 1,000 scientific papers, contributed 2 books, and is the inventor or co-inventor in over 80 patents. His academic journey began in Berlin, where he earned his doctorate in natural sciences and went on to complete a habilitation in physical chemistry before joining EPFL in 1977. Since then, his research has inspired scientists around the world and catalyzed innovation at the intersection of physics, chemistry, and engineering. His global impact is reflected in the numerous honors he has received: 10 honorary doctorates from leading institutions across Europe and Asia, and an impressive list of prestigious awards, including the Millennium Technology Prize, the Balzan Prize, the Faraday Medal, the Harvey Prize, the Ras Nano Prize, and the Albert Einstein Prize, among many others. He is a distinguished scientist at King Abdulaziz University, an adjunct professor at Nankai University, and a fellow or honorary member of numerous leading scientific societies worldwide, including the Royal Society, the German Academy of Sciences, Leopoldina, the Swiss Academy of Technical Sciences, the Royal Spanish Academy of Engineering, and the US National Academy of Inventors. Through his relentless curiosity and commitment to advancing sustainable technologies, Professor Graetzel has profoundly influenced both the scientific community and the global pursuit of clean energy. His legacy is one of innovation, inspiration, and impact. Please join me in welcoming Professor Michael Graetzel.
I'm tall, you can see me.
The microphone?
Okay, well, thank you very much, Mercouri. It's so good to be back here at Northwestern. It's one of my favorite places. I did a postdoc in Notre Dame, and hence I know the area very well. But I was also on the energy program here. I was an external expert, and so it's an honor and pleasure to follow Chad's invitation and give this lecture here. So yeah, I should also thank Mercouri for his kind introduction.
Just need to be on the stage.
I do? Okay. I bow again. It's just awkward with the slides, okay. So anyway. So yeah, and I like to thank Mercouri for his kind introduction, and not last, not least, Margaret Connolly for having coped with many whims and difficulties to arrange my trip here and make everything comfortable. So with that, yeah, the talk will be on nanostructured photovoltaics, and the title slide shows one example. It's iron oxide, rust. Rust, if you put light on rust, it does nothing. Fortunately, it doesn't do anything. However, if you nanostructure it, you will see the oxygen bubbles coming out. And why is that? The design, the nanostructure design allows the positive carriers to escape to the surface before they recombine. They have a very short diffusion length in the nanostructure. But still, you absorb the light by using this cauliflower structure. So it's a very nice example of nanotechnology in energy conversion. Yeah, so I will talk with I shouldn't show this slide. It's on renewable energy and global warming. So I passed on, okay. I was told it's maybe more of a political issue. So anyway, so the green leaf is let's just say that we need to do work on renewable energy, and photovoltaics has a key role to play. We have to increase our installation rate by a factor of at least 10, from 300 gigawatts per year to 3 terawatts per year to meet the Paris Climate Agreement. And so, yeah, so our work is in line with these targets, and the inspiration comes from the green leaf. It's a molecular absorber. And so these tiny molecules and fragile molecules achieve a 92 terawatts. That's power. That's the rate of energy storage. And this is chemical energy storage. And so nature has designed a wonderful system to do that. And so one way to mimic the primary reaction in photosynthesis is to use a sensitized semiconductor concept. So we have a large bandgap semiconductor like TiO2, the white paint, and use the conduction band level of this semiconductor to act as an electron acceptor. And so on the surface, we have a adsorbed sensitizer molecule, a self-assembled monolayer, which will do the light absorption. When light is hitting the sensitizer, the machine gets put in motion, electrons injected, they do their work outside the circuit, and then we get the electron back through a shuttle that has to bring the charges back to the sensitizer. And so we were not the first. In 1979, I met with John Goodenough. At that time, he was a professor at Oxford University. And he had come up with a sensitized TiO2 system where the ruthenium complex was a light absorber. And he had correctly, thought to attach it through these carboxylate groups at the surface so that the absorption would be self-limiting. So you dip the film in a solution and a monolayer is formed, then it stops because all the sites that can attach the molecules are filled. However, the output of this device was very low, 70 nanoamps per square centimeter in equivalent sunlight, which is about 100,000 times less than what a silicon photovoltaic would produce. And so at that time, the prevailing opinion was that we shouldn't touch. As a young scientist, I was told, don't go in this direction. It's a fruitless effort. No chance to get those numbers up by 5 orders of magnitude. And so, but we came from a different angle. We had been working on nanostructured electrodes. And so together with our colleague, Professor Augustinsky, we made a sol gel film of TiO2, which had a fractal, a large surface area. And the first results looked very encouraging. We could get quantum efficiencies, external quantum efficiencies of 40%. That means 40%, a fraction of 40% of the incoming photons of a certain wavelength, a maximum in this spectrum, were converted to electric current, 40%. And so that encouraged us to build a device, and so that gave even better results, 75% of the incoming photons. That was at 450 nanometers. That was not across the spectrum. However, it encouraged us to go further, and first of all, we protected the invention by a patent that was followed by many other patents, over 5,000 by now. We didn't have libraries. We only had the few patents in the beginning, but they brought in a lot of licensing money. And so we could continue our research. And the next generation was a system where we used that was a real nanocrystal system now, where we used nanoparticles of TiO2 that we arranged in an array of say, about 5 micron thickness. And that enhanced the surface area of this film by several thousand times. So with a monolayer of dye, we were able now to capture the incoming light very efficiently. However, the question was how do these electrons, which we might eject in these particles, get collected? And so our physics colleagues, they thought we had no chance to collect those because, for a very simple reason, TiO2 is an insulator. So how come you can conduct electrons with an insulator? So they said, look, your concept is not correct. And when we presented first the data in the literature where we showed 1,000 times enhancement of photocurrent by going from a flat surface to this nanocrystalline film, our colleagues were very skeptical. I remember I was invited to the University of Texas at Austin. The department head called me in his office and said, Michael, I think you made a mistake. And, but you're a rookie, you can still correct it. We'll forgive you this time. And so I said, no, I didn't make a mistake. These measurements are correct. And so anyway, his postdoc wasn't able to reproduce the result. And so then I asked him for the electrode. It looked blue. So TiO2 doesn't look blue. It looks white. Okay, so I had my own electrodes and showed them that the system was working. I was traveling at that time to show our colleagues that these systems were real. And you got those huge enhancements in photocurrent. You can see on the lower right side, you can see that now the quantum efficiencies are over 80%. That's practically quantitative conversion. All the photons in the spectral domain that hit the surface of this film will be converted to electric current with a molecular sensitizer. And so, yeah, I won't go into physics. I don't have time. Why it's possible to collect the electrons. Suffice it to say that the carrier diffusion length, that's it, the length the carrier can diffuse in those films before they recombine with the positive charge, is several hundred micrometers. And so that's much less than the film thickness. And so we could collect those carriers. And so a Nature paper was published in 1991 that got very highly cited because for the first time we introduced this three-dimensional geometry, this three-dimensional mesoscopic structure to convert photons to electric current. And here's Brian and I in a conference in Sweden. And then you can see the extension of the spectrum. Now we cover the whole visible, and we get over 80% conversion. That was by designing the sensitizer structure. And yeah, then organic sensitizers came and took over. Today's cells, we use mainly organic sensitizers. Yeah, and so efficiencies are growing, and the applications are growing too. So a lot of industrial interest since the Nature paper. And we have applications in the panels that collect bifacially the light that helps in the conversion efficiency. We have, for example, our facade in Lausanne still working after 15 years. And I just showed that another example. I'm very proud of this. 10 years ago, we are celebrating now 10 years anniversary of this world exhibition in Milano, and there was a whole wheel that the Austrian pavilion of panels that gave 16 kilowatt power. That was the molecular photovoltaics producing 16 kilowatt power. And the lady you see next to me is my wife. And it so happens that we had my Texan wife, I should say, that she has the same birthday like I on the 11th of May. And we visited on the 11th of May. So we got a birthday cake from the exhibitors. And this is the truck that is run by those molecular photovoltaics. And so a lot of people also in diffuse light applications, I move over that quickly, consumer products, indoor and outdoor. And actually, the Swedish company is certainly a leader now in this area. Yeah, if you look at one of their production sites in Sweden is producing over 1.5 million square meters per year now of those flexible photovoltaic devices that power all sorts of consumer electronics. And but also outdoor photovoltaics. And so you can see the website. They exhibited this year at the Consumer Electronics. It was one of the biggest stands in the main exhibition hall. And consumers are also very happy with the product. So I'm going now on to the perovskite solar cells, which is it's a second revolution in photovoltaics. But it all started with the dye-sensitized cells, because the first perovskite cell was a dye-sensitized cell. The only difference was the sensitizer replaced by the pigment perovskite that Professor Miyasaka had thought of. And so this was an article published in JAX. And I remember I was the referee of this article. And I asked him to study the stability, which was, of course, not very good with these electrolytes dissolving the perovskites. And so the solid-state version became very important. And I should give credit to Mercouri Kanatzidis, who is here, of course, in the audience, our chair, having been the first to publish, and this is a Nature paper on the solid-state version of the dye-sensitized, a mixed dye-sensitized perovskite solar cell. So it's the birth of the solid-state perovskite solar cells. And there was, the same year, there were a couple of other papers published. And so from there on, you see a number of publications going up. In 2012, it's still in the noise level. You can see the point. It's 2 or 3 publications that came out. And today, we have 7,000 per year. So over 37,000 papers have been published over the 12-year period. And so if you want to read those, you have to read 20 perovskite papers per day. So good luck, good luck. So we have to use AI, or we have to go to conferences to keep up with the latest trends. But the efficiencies also have gone up tremendously. I mean, we had certified the first cell in 2014. We got 14%, and then today they are double. They are close to, they are 27%. So within 10 years, the efficiency has doubled. And that's an amazing, amazing success. So I don't want to drown you with now, there's so many papers in perovskites, we could go on forever. I want to focus on our own research, something unpublished and something that relates very closely to nanotechnology. So, but just by way of definitions, there are PIN and NIP structures. So what you see on the left side is a NIP. What that means is the light, the sun comes from the bottom. It's first going through the electron selective layer. A perovskite has a light-absorbing material contacted by one material that only takes the electrons out, and the other material that only takes the positive charge or holes out of the device under illumination. With that, you don't need a p-n junction. This is enough to run very efficient photovoltaics. And these systems can be done or produced by solution processing. And as you can see, the film thickness here, it's a 200 nanometer scale bar, is 1 micron compared to, say, silicon has about 150, 200 micron thickness. So it's much less material, 1,000 times less absorbent material than silicon, but produces now almost the same efficiency as a silicon photovoltaic cell. So, and you can do it, you can make it by solution processing. So that's this power of this technology. That's why so many people are working on it, especially in China. 2 weeks ago, I just was in China. I gave six talks in 6 days in 6 different cities. So you can imagine. So so this is the structure of the cells, and so PIN means the light comes in through the hole selective contact. And so which one is winning? Well, I mean, first it looked like the NIP was always the head, but recently there's almost same efficiency. PIN slightly leading in the range over 26%. So yeah, so there's a lot of research now on the materials innovation. However, I want to focus the rest of my talk on the alpha formamidinium lead triiodide. Why is that so important? That's the best absorber material. There are many mixtures and compositions. But if you want to convert sunlight to electricity, you would use the formamidinium lead iodide. I think Mercouri would agree with that. It has the best optoelectronic features. It has also high temperature stability. And it's water sensitive, but so are the other perovskites. They're ionic crystals. And so you would like to use that, but the alpha phase is not stable. It has a phase transition at 160 degrees. So a photovoltaic cell that can only run above 160 degrees is valueless. And so, you need something that works at room temperature, maybe up to 100 degrees. But so a lot of research has been invested into avoiding that phase transition, which turns the black phase into the yellow delta phase. The delta phase is a different structure. It's a one-dimensional structure with hexagonal symmetry, and the octahedra are phase sharing. So it's a different structure than these corner sharing octahedra you see in the alpha phase. And so a lot of interest was research interest in maintaining the alpha phase stable. You can do this in different ways. You can add foreign ions like cesium or other acations. But of course, the nicest thing would be if you could do it just use pure material and still keep it alive at room temperature. And so this is possible by different ways. I'm now using the sequential deposition. What is that? Well, you would first put the lead iodide on your conductive support, be it hole selective or electron selective. And then you would have to convert it by reaction. The reaction is written up there with formamidinium iodide. So that conversion reaction works. It's described in a paper which we published in about 10 years ago. And so there we used the titanium oxide, this nanocrystalline film, the same we had used for the dye-sensitized cells. And the conversion worked so well because you would use the precursor. The lead iodide would partially fill the pores. There was a high surface area exposed of the lead iodide. And so the reaction with this conversion reaction would go on very quickly. However, the real interest is to make compact film, so formamidinium, not mesoscopic films. And so here's some unpublished work, which I will now go in for 5 minutes in more detail, so to give you the taste of our present efforts. So how can we then make phase pure and also the composition pure FAPBI3 films from using this conversion method? Again, I mean, the challenge is you have on the right side, you see the start with PBI2, which has a corner sharing octahedra. And so if you want to convert this to the formamidinium lead iodide, you have to break one lead iodide bond. And you get the corner sharing octahedra. And that reaction is catalyzed by chloride. So we added chloride, but we also made the films very thin so that the formamidinium could penetrate very quickly across the lead iodide. If you would have a thick layer, a planar layer of lead iodide, the conversion wouldn't work well. And so we used 2 nanometer thick PBI2 sheets. How do we make those? Very easy. You use a PBI2 conversion. You put it in an ionic liquid, methyl ammonium formate. And you can form these thin sheets. You first form actually the formamidinium lead iodide, but on heating it decomposes and you get these nanosheets. And so, and now you see how fast the reaction goes. You see the second, on the bottom, you see the absorption curves. They reflect the kinetics of forming the desired form armadillo iodide. You see, within a second, this reaction is over at room temperature. And you get the phase pure material. That's the miracle of nanotechnology. You go from those nanosheets, you add a catalyst, in this case, the butyl ammonium chloride, and the reaction is driven at a phenomenal speed so that you instantaneously form the black phase, which then is stable. And you can see actually the conversion can be monitored optically, but also by doing time-resolved GVAC studies. And you see that this new phase shows up within seconds. If you use bulk PBI to it, it doesn't work well. It doesn't convert well to the desired form armadillium perovskite. And here's another very interesting feature. You can form these black films, the lead iodide films, even in rainwater. Usually they're very humidity sensitive. And so how is that? Well, we have the butyl ammonium cations on the surface. They're hydrophobic, and they reject the water ingression into these films. And so you can see here we are heating the film at 150 degrees in 80% humidity at 150 degrees. I mean, if you put your hand in a climate like that, I wish you good luck. And so these films survive. These films survive under these conditions. So that allows to make these devices even in rainy conditions. So, and stability-wise, you see very nice operational stability. Efficiency is over 26%. So, paper is submitted. Let's hope the referees will like it. And so with that, I think I've come pretty much to the end of my presentation. I'd like to, first of all, mention to you, we do have a project in Adana, Turkey, to build a production line where we use a carbon contact. A lot of people use metal contact for the capturing the electric current. But we went to carbon, so we have developed also specific forms of carbon that would work very well for those perovskite solar cells. And yeah, here's the team. The Guinness is actually a pretty old company. They're existing since 2012. And the founder, Gisa Vedat, is actually a very distinguished businessman in Turkey. But he has a real passion for perovskites. So he wants to absolutely set up this production line. And fortunately, today, you can buy a production line for perovskite cells turnkey in China that gives you 20% modules, a minimum efficiency of 30 by 30. That's where the technology stands today. You can buy turnkey pilot lines in China that bring out those panels. You see how the Chinese have been pushing that and how successful they are in putting this technology to work. So with that, I'm at the end of my talk, and thank you for your attention. This is our group photo. Behind our group, you see those panels? These are the dye-sensitized solar panels that are used on our facade, the Swiss Technology Center in Lausanne. Yeah, with that, I think I'm at the end, and we are very fortunate to live in a beautiful site like Chicago next to a lake. So with that, again, Chad, thank you very much for your invitation, and Mercouri for your kind introduction, and thank you for your attention.
Thank you, Michael, for the great talk that you gave and introduction and the progress in the field. Now we have time for questions. Please signal for a microphone, and then if you have a question, and then stay standing so that the speaker can see you. one there. Cheng?
Thank you, Michael. So I'm Chen. I'm postdoc in Mercouri and Ted Group. So I wonder, so you have a lot of experience in the dice solar cells, so and improve the stability a lot. And this is also like organic material-based solar cells. So for perovskite right now, we also face the stability issue. So do you think is there any lesson we can learn from the solar synthesized solar cell, and it can be used for perovskite solar cell? Yeah, that's my question.
Well, thank you. Yes, in many ways we can learn, but the perovskite solar cells are more challenging than dye-sensitized. The dye-sensitized, you can't kill them. I mean, if the dye is on the surface and you have something that regenerates it, they will work. And even if that dries out, you put a little bit of ionic liquid back and they will run again. The perovskites are much more complex. I mentioned the compositional complexity, structural complexity, and so, however, it's amazing how stable they are now. I mean, I haven't cited the work of some of our colleagues. We are running now 85 degrees, the so-called ISOS L3 test. That is 85 degrees centigrade on the cell all the time. And then we have full sunlight on it. And then we have maximum power point, which means electrical stress across the cell. And some people now get 2,000 hours. Imagine you're in a sauna 85 degrees for 2,000 hours. And they just lose very little, a few percentage points. So the extrapolated lifetimes are now, because these are accelerated tests now, are they giving the whole truth for outdoor? We also have to do outdoor testing, and that's going on. And the day and night circle, you certainly have to do the temperature cycling. It's very critical for perovskites. But also there, I mean, no red flag has come up so far. Okay, and so the progress has been enormous on the stability front. And so the only problem that is left is the lead problem. And so we have to put those cells in a solar farm and maybe on the roof, okay, and have some fenced in, because for consumer electronics, they wouldn't be a good choice, in my opinion.
Another question? I have a question. You mentioned that there's a Chinese company selling a panel 30 by 30 centimeters or so. What stability are they claiming?
No, it's misunderstanding. They're selling you equipment, a line to make those panels.
Oh, equipment. Okay.
You can also test now these panels. Last week I was in Stuttgart. There was a perovskite conference organized by Nature, the Nature journal. And Michael Saliba was running it. And so at the end, we had a whole number of industrial companies presenting. And so, but also Michael had tested the panels that a company in Shanghai is producing. And Hairan Tan is the founder of this company. I know him very well. Yes. He's a scientist also. He made very important contributions to tandem cells. And so, yeah, so this Remschein company is now handing out panels. These are big panels, 60 centimeter times 120. And I asked Mike, he has had some of those panels on his roof at the institute. They have a huge photovoltaic institute in Stuttgart. And they have all the techniques to do measurements correctly, and all the people that are highly trained, so on. So I trust. So anyway, these panels have been lasting now for 1 year, and there has been very little change in efficiency outdoors.
Recently, I read that Oxford PV, another photovoltaics perovskite company, is claiming 10 years.
Now the issue is the following: if you have compared to silicon, then silicon degrades 0.5% per year. So in 20 years, you have 10% degradation. I don't think that the perovskite cells are there yet, but think about the tandems that have now reached 34.9% with silicon. If you could buy a tandem that produces 30%, my silicon panels give 20%, okay? 30% efficiency, there's certainly a market if they last for 10 years.
Yes, I see.
There's no doubt people are so much hungry for power. With all these power centers and the AI and stuff, we need so much electric power. I think I would invest into, I have already, I should say. So there's no doubt that this technology will come, given the forces that are now behind and the issues that remain to be met. It's not, we are not quite there. You cannot buy them. The Dyson styles you can now buy in products and as such, but the perovskites you can now test. You get test panels, and you can buy the lines that make the perovskite with certain warranties on efficiency.
Amazing. Yeah. It's great that progress is being made. I think it has a good sense of getting there in terms of decadal stability. Are there any other questions? Yes, there's one there.
Hello, I'm Samira. I'm in the Kayla lab here at Northwestern University. I was wondering if you looked at, when you were looking at those sensitizers binding to the titanium, if it was more important, like the functionalities on them that allowed them to bind to the titanium and do efficient photosensitization.
Oh, the co-sensitization?
Like if there was any different structures you looked at that bound to the titanium in different ways.
You mean for the DSCs now, dye-sensitized?
Yes.
Yeah. Yes, I believe that the invention of that was made at Monash University by Rachel Caruso, the nano beads, these are probably the best nanostructures for dye-sensitized cells. They're about 500 nanometer to, you can adjust the size and the pore radius. However, they have a very big advantage in the sense that you can heat those materials and make them perfectly crystalline, and then you make the film, okay? So you're not limited by your support that may or not tolerate high temperatures. And also, they have this bimodal pore size distribution here. You have macro pores, so diffusion between those beads is fast, and then you have the channels. And so the diffusion limitations, which sometimes play a role in dye-sensitized solar cells, are much less there, and very good light scatterers. So all the features are there to make it there. I have tried I'm still trying to convince my coworkers and to make those beads. And we have collaborated with Rachel. And actually, I just saw her recently in Brussels, and she told me she would help us. Okay, so that's a good question. Thank you.
So there was one question here. One there.
Hi, Matthew. I was from GTI Energy. This is probably outside your expertise, but silicon solar seems to have such a head start as a technology. Have you looked at the learning rates on thin film technology to see if at some point it's going to compete openly with silicon solar, or will it only be through tandems that it will enter into those markets?
Yeah, that's a very good question. I have a whole talk on comparing the perovskite to silicon. And let me tell you some of the caveats that silicon has. Okay. The one is just the pure weight. I mean, for 1 megawatt, you need 7 tons of extremely pure silicon. There are 9 nines in the purity figure. Now, the perovskite, you can take the stuff from the shelf and do solution processing. So the energy payback time is also long for silicon. And they use coal to produce that energy. So there is a big carbon footprint. All this, and finally, to top it all off, the recycling is very difficult. The price of silicon for recycling is $50 per panel. putting them on a landfill is $5. So I could give you a whole hour of arguments because this is a question that comes very often. And I think, yes, there is a very good chance that these panels, the perovskite, will become a competitor on the single junction. It's just that at the moment, people see, the low-hanging fruit. This is a 30% panel I can sell and so on. But that doesn't mean the monojunctions are not being developed. The plant I showed you in Turkey, that's for monojunction. Carbon, using carbon as a back contact material.
So thank you, Michael. So if there are more questions, you can catch Michael Graetzel during the breaks to ask him those questions. For now, please join me in thanking Michael Graetzel for a great talk.
Hello, everybody. My name's Ted Sargent, and I have the great privilege of introducing our next speaker for today, which is Professor Sir Richard Friend. Richard completed his undergraduate studies and also went on to do the PhD at Cambridge University in physics. There he worked under the mentorship of Professor Abe Yoffe, whose work is often described as being on the borders with chemistry. During this period, he had a pivotal research fellowship, which brought him to the University of Paris, where he spent a year working with Professor Denis Jérôme. It was there that he made a sharp and defining shift in his focus from inorganic materials to molecular systems and carbon-based conductors, laying the foundation for a great deal of his ensuing work. Today, Richard is known as one of the world's most influential materials physicists. He's made groundbreaking contributions to the physics and engineering of carbon-based semiconductor devices. He's currently a faculty member in the Department of Physics at the University of Cambridge. He's also a fellow of St. John's College. He's founding director and special advisor to the Maxwell Center at the Winton Program for the Physics and Sustainability, the Physics of Sustainability. And he's co-founder of a number of university startups, including Cambridge Display Technology, CDT, which I think many of you know. Richard's work has really revolutionized the understanding of molecular semiconductors, demonstrating their suitability in electronics and paving the way for their use across fields like solid-state light-emitting devices and polymer LEDs. Beyond academia, Richard has expanded the impact of his research through entrepreneurship. He's founded multiple companies. He has over 140 patents and 1,100 scientific publications. And he's really regarded as a key pioneer in the field of plastic electronics and in advanced optoelectronic systems. He's won many awards, more than I can name because I want to leave a little bit of time to Richard today. But Richard's extraordinary contributions have earned him things like being knighted in the 2003 Queen's Birthday Honors for his services to physics. He's also a fellow of the Royal Academy of Engineering, the Royal Society of London. He's a foreign member of the US National Academy of Engineering. He's an honorary fellow of the Royal Society of Chemistry. And his accolades include laureate of the Millennium Prize for Technology and also the Harvey Prize of the Israel Institute of Technology and the Von Hippel Award of the Materials Research Society in 2015 and the Isaac Newton Prize of the Institute of Physics in 2024. Please join me in welcoming Sir Richard Friend.
Well, Ted, thank you very much for those warm words. It's a real pleasure to be at Northwestern. I have many great colleagues here, and it's just so exciting to learn a little bit about what's going on in this tremendous organization of nanotechnology. It's so important that somewhere people stand up and be counted, and to see how well that's gone, how this big, determined effort to take science through to usefulness is so important for all of us. So the title I've got, which is, I hope, more intriguing than the placeholder title that's in the program, is really around the fact that if you take a semiconductor, or most molecules that have some color, if they don't glow, throw them away because they're dirty. We've been misled by silicon. Silicon, like a Model T Ford, is black. Even if it did luminesce, you wouldn't see it because it's in the infrared. But by the time you go to something that is colored, that you can see, it's red, green, or blue, if it's pure, if you've engineered it correctly, if you've taken out the non-radiative decay channels, it should be luminescent. Now, if you look through the catalogs of molecular materials, you can find many isolated molecules that are very luminescent. We used to make dye lasers with them. They're used for fluorescent tagging for confocal imaging in the life sciences world. But if you want to do something more challenging, which is to put them together because you want to turn them into semiconductors to move charges into them to make a light-emitting diode or pull them apart in a solar cell, life gets much harder because there are so many pathways that can stop them being bright. So I'm going to start with an image of something pretty familiar. I have to say this isn't this year's model of iPhone. The organic light-emitting diode, and you have millions of those on your smartphone, must be the second most produced semiconductor device material after silicon. It is now the dominant display technology. Back 30 years ago, when we were first making some of these or discovering how they could work, they lasted a few minutes or hours. It is remarkable how well they have been engineered. I'm not going to give a talk about how to make OLEDs in particular, but I do want to concentrate throughout this talk on how much work has been done, but how much work there is still to do on keeping the luminescence up. And actually, there's a particular problem if you're bringing charges together that when they recombine, when electron meets hole, they can form a spin singlet configuration, which will be luminescent or fluorescent. But spin statistics mean that if the electron and the hole had the same spin, they can form a spin triplet state, in which case, if we were lucky, we'd see a little bit of slow phosphorescence. And that is bad. So I'm going to show you a device, a working device, because why not? It's a device that was made in Cambridge 20 years ago. And what you can see on the left is something that looks like a transistor. We have a substrate. We have a green layer of light-emitting semiconductor. It's a polymer. The chemical structure is at the bottom of the screen if you would like to check that out. The yellow bars to left and right and the thin one on top are gold. They're acting as the electrodes, and it's a field effect transistor. But we can actually run it so that we can simultaneously inject electrons and holes from the source and the drain. And in various ways, we can adjust source, drain, and gate voltage to make it a light-emitting transistor. So what you can see as the gray-black bars are the interdigitated electrodes for the source and drain. It's about a 20-micron channel length. And as I run the video, you can watch as the line of the point of recombination where electrons from the source meet holes from the gate, we get light out. And you can see slightly crystalline, and you can see some fringe fields around the edge as we swing the line of light formation where electron meets hole across the channel. Eventually, it fizzles out, inevitably. So this is a wonderful video. It hasn't produced a technology that I'm aware of, but it does just show you in one little video that you really can use molecules to do everything in electronics. So back to the real business, and that's spin, and how spin gets in the way of luminescence. So the scheme on the left shows a ground state singlet, which is where most molecules are. There's an excited state singlet, which we can photogenerate, and these materials, if we got them right, will luminesce very efficiently. But electrons and holes coming from opposite electrodes, their spins with respect to one another will be random, and 3/4 of the electron-hole collision events will be triplets. And because the excited states that we have on these molecules are quite confined, the exchange energy is usually large, much more than a thermal energy, so we get dark triplets. Now, if that was all that could be done, there would be no OLED technology in your pocket. What has been done so far is to get the efficiency of the red and the green subpixels up to close to 100% by actually getting them to phosphoresce. Mark Thompson, Steve Forrest, when they were at Princeton, sorted out how to use organometallics, and this is an iridium complex where the phosphorescent lifetime is quite short, about a microsecond, and that does red and green. Blue is not fixed. The blue subpixel has got an internal efficiency that is sort of 25%, not 100%. The best that is done with current technology is to pile up the triplet excitons in the device until the population gets large enough that the dominant decay for the triplets is that they fuse. If they happen to be overall spin 0, 2 triplets can fuse to make a singlet. And then you can get blue out, and that is engineered in. It's quite unusual device physics, but blue is not sorted. Okay, so what can we do? And I'm going to give you some stories of things that have happened in Cambridge in the last couple of years. Chirality is easy to say, hard to deliver. So what can we do with it? Well, we've had a project running with Bert Meyer at the Technical University of Eindhoven, and Bert has built his wonderful scientific story around chiral control of supramolecular systems. This is, I think, true nanomaterial science. And we were actually jointly funded through a European Union student training program, so we had a very, very good collaboration. Working with these molecules, TAT stands for triazotroxine. You can see the core, which is planar. And around that, we've got side groups on the left, with the S-TAT is a chiral side group, N-TAT is not, Fen-TAT is not. And rather magically, what happens is that they stack to form columns, but the electronic structure of the individual molecule is not very chiral because it's really just in the planar bit in the middle. But when they form columns for the chiral system, the chiral side group gives enough push to set up a chiral three-dimensional structure. So it's my student Ritipano Chowdhury managed to make crystals and solve the crystal structure for a huge unit cell. But what it boils down to, and so the lower image is that the repeat unit is just 6 of these planar molecules. By themselves show very little circular dichroism, but get them to twist. So we get 120 degrees twist by the time we've got up 6 molecules, and they're quite close together, so they interact quite well. That is a chiral semiconductor as opposed to a chiral molecule. Now, this is the technical bit on the left. Because we have a crystal structure, we can calculate the electronic structure. I have some wonderful colleagues, Josh Thompson, Tommy Montserrat, in Cambridge Material Science. And what they've calculated is what a chiral variation of electron or hole energy level is with momentum. If you look on the right-hand side, the red and the green bands are bands that are chirally selected. They both have orbital angular momentum, as you might expect. They describe circularly polarized electron states. The one that has more dispersion is the one that spirals in the same sense as the crystal spiral, the one with less spirals in the other way, but they're differentiated away from high symmetry points. And you can calculate the optical transitions between these chiral electron and hole states. And yes, they are circularly polarized. That is to say, the photon that comes out has a lot of circular polarization, as you can see on the right. So it really is a useful chiral semiconductor, but it's just a little single crystal which isn't much use. So the surprise discovery is that if we try and make organic LEDs, which usually involves putting the emitter into a host that transports carriers but is a wide gap, a strange thing happens. As we co-sublime in the middle of the panel, we get isolated molecules. They emit blue, but with a little bit of heat treatment or passing electrical current through, we get a local crystallization within this high TG matrix, and locally we get little chiral regions, and as they form, the luminescence switches from blue to green. We've got the chiral structure, and we've got a thin film, which is chiral, and we can now put that into the middle of the sort of stack that is used for a standard organic LED. So we were happy to do that. We could get quite good circular polarization of the electroluminescence, which is good. But there was a surprise. And let me start with the achiral material that we've used, which is the FenTat. What we would expect, because this material has a luminescence yield of around 50%, that the external efficiency of photons generated by electron hole capture should be a quarter of 50%, which is down at about 3.5%. A quarter because of the triplet fraction, 3/4. A quarter because only a quarter of photons generated tend to get out in the forward direction. So we should have got 3.5%. We measured 2.9%. But when we used the chiral material, we got the factor of 4 from the singlet versus triplets back. We're up at 15%. If we had 100% PLQE, we'd have had 30% external yield. But that is a high number, and we don't know why it works. Broadly, it looks as though when we've now got orbital angular momentum in the mix as well as spin momentum, we have an overall J, and within conservation of J, it turns out that everything is luminescent. And we found what, rather surprisingly, it looks as though adding in chirality might have unlocked that problem of getting photons out irrespective of how the electron hole capture takes. So that was one. Let me carry on the journey. And now we're going to forget chirality. I'm sure we'll come back to it one day, but now add a spin. So rather than starting with a material where the occupied orbitals are doubly occupied and the unoccupied orbitals are empty, that would cause a closed shell system, what happens if we start with a molecule that is a radical? Now, most of you will say, radicals, forget it, they're bad for you, and they do chemistry. And in general, that's true, but in particular, it's not. If you want to avoid chemistry, you need to wrap them up so that if they bump into one another, the two radical sites are too far away from one another to do covalent chemistry. And this sort of the triphenyl methylene structure sort of wraps itself up in a sort of chiral little propeller, and it's been known for a very long time as quite a stable radical. But most of the literature on radicals is that they're dark. They're enormously interesting. They're very serious candidates for secondary batteries, for rechargeable batteries, because redox involving radicals can happen very efficiently and surprisingly stably. And back to the stability, the electronic stability just depends on where the energy levels are for oxidation and reduction. And if they're at the same sorts of energies as we are quite happy with for the sorts of molecules that are in standard OLED displays, we don't have a chemical instability, a sort of instability associated with them being very hard to access electronically. TTM does that, but it's dark. So there was a very interesting paper in 2006, Gamero et al. From a group in Barcelona in Spain, They hadn't made exactly this molecule, but this is one that we've been working with, Kanatzidis link with the group of Fong Li in Jilin University, where what's been done is to attach an electron donor. It's a carbazole. That's the red bit at the bottom. And it suddenly becomes bright. I mean, they weren't that bright then. They're now, many of them are close to 100% luminescence yield. What happens with this carbazole system is that the optical transition is transferring an electron from the lone pair on the nitrogen, a non-bonding level, to the singly occupied methylene carbon, the radical, that's the black dot at the top. That transition, that charge transfer transition, is relatively allowed, and it gives a very nice deep red emission. Here's the same molecule on the left. On the right is its luminescence spectrum. You see it luminesces with a peak just beyond 700 nanometers, so it's deep red. Rather surprisingly, I mean, most molecular materials are very good in the blue and the green as fluorescent materials, as phosphors, but they're lousy by the time you get to the infrared for reasons I'll touch on, but this bucks that trend. So in the middle, the panel in yellow shows on the left the ground state, where we have 2 electrons in the highest occupied molecular orbital, which is the lone pair-centered orbital on the carbazole. And then we have the SOMO, the singly occupied molecular orbital for the radical at the top. And the optical transition goes from left to right. We simply go up and down within the doublet manifold, and it's bright. So what happened to the triplet? Well, the triplet is now a quartet, but it's higher energy. The lowest quartet we can draw, you can see on the right, we have to now occupy the lowest unoccupied molecular orbital, which is 1.7 eV higher in energy. So just by changing the state fillings, we have rearranged the levels, and we've now got a general class of materials where the lowest excited state is bright. So that's fantastic for making LEDs. There's no triplet problem. We can make very efficient LEDs with these, and it has broader implications. So why are they so bright? This is a sort of small deviation from the thread of the talk that I want to take you through. But we were puzzled. What our materials seem to do is to buck the trend of what's called the energy gap law. That as you head from blue or green, where you can get very luminescent materials, to red and infrared, molecular systems just stop glowing. And the reason in general is that because we have lots of high-frequency vibrational modes, the carbon-hydrogen stretch at whatever it is, more than 3,000 wave numbers, it doesn't take many vibrational quanta to get you right across from the electronic excited state back to the ground state. And as you go to lower energy excited states, as you go to the red and the infrared, that takes over. That seems to be switched off in the materials we designed correctly. So this is a cartoon, a figure or two from a paper that we published last year, where there are 2 molecules. I apologize if it's an awful lot of chemistry there. To a physicist like myself, I have to have it explained to me what the difference is. But one of them has got a luminescence yield of 14% and a relative lifetime of 3 nanoseconds on the left. The other one, in toluene solution, has a luminescence yield of 92% and a much longer emission lifetime because there's less non-radiative competition. So why switching the point of connection on the carbazole to the TTM group does it change? Well, the answer is that what it has done is to tip the HOMO state from being a state primarily of nitrogen non-bonding character, which is the one on the right, to one that looks like a pi bonding character, and that then couples very strongly to high-frequency ring stretch modes on the phenylene bits, and that switches on vibrational coupling. So if we have the design rules, which are set out very carefully in that paper, you can actually engineer luminescent materials down in the red and the infrared, which is pretty useful if you want to head towards the biological window, sort of centered around 800 nanometers. So we have done a lot of work with spin monoradicals, seeing what we can do with them as standalone, very luminescent objects. And for red OLEDs, they look a pretty good option. What happens if we couple spins? Where should we start? Well, I'm going to change gears a bit. This happens to be drawn one-dimensionally because it takes up less space on a screen. What happens if I take a load of things, atoms, molecules, each of which has got a singly occupied orbital and therefore has got a spin, and bring them into contact? Let me define that contact by some transfer integral, some amount of overlap of electronic wave function. And that is a structure that was much studied for transition metal oxides. It's what is generally called a structure that, if it has those localized spins, a Mott-Hubbard insulator. If you take the undoped high-temperature superconductors, the cuprates, the nickelates, they're antiferromagnetic because the Coulomb, the cost of putting 2 electrons onto one site, and you can see that's the middle of the lower line. If I doubly occupy one orbital, it costs a Coulomb repulsion energy, usually called the Hubbard U energy, which is quite large. And unless I bring the spins really close together so that the band formation described by T becomes larger than U, I'm stuck with an insulator. And by the way, the reason I've drawn it antiferromagnetically is that transfer from one site to another can only happen if the electron and the electrons in the 2 sites are in a singlet state. It can't happen if they're in a triplet. There's some spin selection, and that sets up an exchange interaction, which is twice T squared over U. It's antiferromagnetic for these simple structures. So that's an area of physics very much studied, where you have to live with high Coulomb interactions. Do our molecular systems have anything to say about that? Well, yes. The lowest energy excited state, when we bring our radicals together, is exactly the same excited state that defines the physics of high temperature superconductors. It's the Hubbard U. The extra we bring to the story is that transition, which apparently is just moving an electron from one site to an identical wave function adjacent to it, but where there's already an electron, so it's higher in energy, it's radiatively coupled. Because there's a dipole involved, it's optically accessible, and it shows up very clearly in luminescence. It sort of must have always been known, but never actually noted in the metal oxides. So I'm going to start with a story about photoconduction. And here we have, it's a radical molecule which has got 3 phenols on it, P3 TTM. And we're going to make films of it where we set up the concentration of that in a host so there's some contact between them, but not so much as to kill all the luminescence for the time being. On the right, you can see 3 different colored plots. They're absorption spectra. The material by itself has strong absorption to about 400 nanometers. If I reduce it electrochemically, the anion absorption peaks at around 600 nanometers. If I oxidize it to form the cation, there's a new absorption. It changes color, and the absorption is now at about 780 nanometers. So I know if I've got electrons or holes on that molecule because I see the color change. Let's photoexcite. There's only one molecule that's there to absorb light. If you look at the panel bottom right, I'm sorry, there are quite a few lines there, they show a time progression from around a picosecond out to 2 nanoseconds. The band on the left at around 500 is an excited state absorption of the exciton. That decays, and what grows in its place are the same 2 bands of cations and anions. So we've taken the same molecule, absorbed light, and it's separated charges all by itself. We didn't need a heterojunction. So can we turn that into a device? And we can. We better start with a control device, which is a heterojunction between rubrene and C60. The rubrene is an electron donor. The C60 is an acceptor. And if we just make a layer-by-layer device, we get about a 10% charge collection because only light absorbed quite close to the interface works. If we go to our bulk TTM radical, we can extract all the charges. We have 100% quantum yield for charge collection. We need a bit of field to do it, but we've now managed to throw away the heterojunction, the donor-acceptor interface, which has underpinned everything we know about excitonic photovoltaics. I'm not saying that's going to tomorrow transform how we make solar cells, but it is certainly another avenue to explore where we've just played around with spin. So finally, and here we sort of have stumbled into a world where a great center is the wonderful work of Mike Wasilewski in this university, who's been publishing parallel but different papers with us. But let me start with some work we've been doing for the last couple of years, where we've got a diradical. I'm sorry the chemistry is looking complicated, but it's 2 of these radicals connected via, in this case, it's a meta-linked fluorine. And it adds in some connection between the 2 radicals that allows some optical activity. These are very, very bright. They're close to unity luminescence yield. I mean, here is a sample excited down a light pipe with some blue light, glowing very, very efficiently in air. These are measurements that Alexei Cheplyansky in Paris was doing on these materials. If you look at the emission spectrum, there are 2 bumps to it, which looks like standard vibrational contributions, and one might have thought nothing of it. But they actually have a different origin. The origin of the red at around 630 nanometers is from when the molecule started out as a triplet ground state. The very red shifted to 700 nanometers is when the ground state happened to be a singlet. And the photoexcited state is that charge transfer state, that Mott-Hubbard excitation, where we've moved an electron from one side to the other, and the energy of that is the charging energy. It's not an electronic gap, it's the Coulomb charging energy, about 1.8 eV. That is the 700 nanometer emission. It comes out efficiently, but more slowly. So what we've got is a tiny difference in energy in the ground state between whether the 2 spins are parallel or antiparallel. Down at about a Kelvin is the exchange energy for this system. But that completely controls a color shift of about 300 millivolts or 250 millivolts. It's huge color shift because it simply acts as a gate. If the 2 spins were triplet, it can't do that and form the lower energy 700 nanometer emitting band. So that's what you want for a spin-optical interface. This is not a nitrogen NV center, but it's the same space where we want to be able to couple some tiny energy difference within the spin system to control what the electronic states are. And here we see it. I will go past that. Now, most recently, and this we put up on arXiv earlier this week, we've been looking at systems where it's a different bridging unit, one actually very close to the beautiful papers that Mike's group published last year and this year. We've done some different chemistry, and we've managed to keep these very bright. Again, high, 80s and 90% luminescence yield, so they're great. Very surprisingly, we have quantum effects. I should have said, I forgot to say that the color, the right-hand side, the way we could switch between the triplet and the singlet was to take the device down to a low temperature and apply a magnetic field to switch the spins from antiferromagnetic at 0.25 Kelvin to ferromagnetic by applying 7 Tesla to swing the spins around. Should have said that. So that paper was all about low temperatures. We've now got things happening at room temperature. And the huge surprise is that there's a massive change in luminescence with very weak applied magnetic fields. The right-hand panel shows that within 2 millitesla, which is down at it's tens of times more than the Earth's magnetic field, but not much, we can get up to a 10% modulation of the luminescence. So if you want to be able to tell whether you've got something embedded in something biological, and you can see it blink, see its luminescence modulated by simply bringing a magnet near it, that's not very high technology, and it looks quite useful. In detail, it's all to do with changes in the ground state between the 3 sublevels of the triplet, and that you can pick up with optically detected magnetic resonance. There's some, I have to say, we've been working very hard this year to track it down. We've had a wonderful collaboration with Sam Baylis's group in Glasgow and Alexei Chepliansky in Paris, and we've separately reproduced this in all 3 places. A particular tribute to Ritipano Chowdhury, who absolutely drove this work in my group. But that is, if you like, the nuts and bolts of showing what we've got. So why are we so far away from most of the nitrogen NV world? Well, the answer is that the magnetic resonance frequencies are radio frequencies. They're NMR frequencies, not ESR, because the 2 spins are far apart. So the energy scale, which is set by the dipolar interaction between the spins, is usually up at gigahertz when they're close together. Here, they're a nanometer apart, so it's down at 50 to 100 megahertz, which corresponds to the 2 millitesla. So it's that very short separation that is super important to give this very low field sensitivity. The closest that we feel we are is to the wonderful work due to, in Oxford, it's Peter Hoare, but others, on understanding migrating birds measuring the Earth's magnetic field using singlet versus triplet photogenerated radical ion pairs, where again the key is if they're far enough apart, very weak fields can set the overall spin state, and that then turns out to have chemically useful effects. This was a little video that Ritipano made actually last Thursday, because I thought it would be fun to do it. So what you can see on the right, looking purple, is our diradical film. It's in polystyrene. It's in air. It looks purple because it's both showing scattered light from the blue laser, but also red luminescence. It's around 630 that you can see easily. On the left is our recording channel on a laptop. And when I run the video, you can see Ritipano bringing down, it's a little glass tube, if you look on the left at the screen, in which he's got a fridge magnet. It is literally a fridge magnet. It produces a couple of millitesla at 3 centimeters separation from the, at a distance of 3 centimeters. And just bringing up, it's really high tech, as you can see. You have to pay the research student. But it's such a surprise to see something happening so easily. It helps that it's bright, and I would claim that it is, it's all that trajectory about learning what we have to do to keep things bright, even though we're adding in extra complexities like moving charges around and controlling spin. I should stop by putting some acknowledgements up, as one's supposed to do these days. Primarily the European Research Council, which is a very good reason for being in Europe. It is wonderful, very unconstrained money, but we have other funding sources too. I'd be delighted to answer questions. Thank you very much.
We do have time for questions for Richard. So please, yeah, we got a hand up back there, and there's going to be a mic coming your way. A mic is coming your way.
Hi, thanks very much for your talk. I'm wondering if you guys have ever observed a difference in response based on the orientation of the magnetic field or the orientation of the material?
It's a really good question. We haven't worked out how to crystallize these molecules yet, and it's on the list. But I'm afraid we're just going for the low-hanging fruit. But super question, and yes, it absolutely should make a difference. Thank you.
Thank you.
Thanks for the next talk. I have two questions, actually. The first question is in the chirality addition in the LED part. So what is the efficiency, quantum efficiency of polarized emission compared to the total quantum efficiency? Yeah.
Well, I showed that this asymmetry factor, which is is a measure of the ratio of the two polarizations, and the largest number we had was 25% for the freestanding crystals. It's a bit lower in the films we've got at the moment. And it's tricky, in principle, to get circular polarized emission in a LED diode because any reflecting electrode ought to screw up circular polarization on back reflection. So it's something we keep thinking about.
Okay, thank you. My second question is about the M2 TTM part. I saw that there's two emissions. One is the triplet extone. One is the singlet. I saw that the triplet seems to show higher energy than the singlet, which is
the triplet is higher. You have to throw away everything you were taught as an undergrad. So let me just spell it out again. The triplet is really very similar to an exton on just one radical. It is a regular exciting a higher lying molecular orbital involving the pi stars, okay? The singlet doesn't do that. It just uses the non-bonding SOMO orbital, but we rearrange from 1 on each site to 0 on one and 2 on the other. So its energy has nothing to do with pi star states. It's a Coulomb repulsion term. In physics speech, it's the Hubbard U. And obviously, if it were higher than the pi star state, we wouldn't see it, but it's lower, and we do see it. The magic is that it's still luminescent, even though it's quite slow.
Okay, thank you.
Hi, Cecile Chazot, Northwestern University. I have a question about your chiral supramolecular self-assembly. Do you see a compensated mixture of left-handed and right-handed once it supramolecular self-assemble, or do you see a single chirality mixture?
Right, okay. So if we use R or S TAT, my experts, Bert Meyer and his group, are very confident from the various imaging methods we've used that we have only one chirality. On the other hand, if we take the N-TAT, which is not of itself chiral, it turns out that it either assembles right-handed or left-handed regions. We can do that from Mueller matrix imaging. And it also gives the enhancement in electroluminescence, whereas the FENTAT simply doesn't form a chiral stack. So we've been looking at those differences, but great question, thank you.
So in one point during your talk, you talked about this issue about coupling of orbital angular momentum to spin angular momentum.
Yes.
And so, but an important issue there just is how long does orbital angular momentum really survive in a complex molecular environment, having to do with the issue about can you emit, there's an emission lifetime, and then there's this sort of relaxation of this coupling of orbital and spin angular momentum.
I think this is sort of early days. I think that for us, I mean, there's plenty of literature on molecular systems where you put in some chiral agent and you get some CPL.
Right.
What we've got here is a single crystal. We've solved its structure. We've calculated its electronic energy states. And we've actually, for me, this is the first time I've understood what chirality can do to split energy bands.
Okay.
My theory colleagues can use a whole load of fancy techniques that I can't say I deeply understand. They can calculate the matrix elements that couple to circularly polarized photons, and it really is there.
Yeah.
So I think a way to explore your question, but my language, is to what extent is a three-dimensional, or in a case a one-dimensional band structure, relevant when we got to molecular assembly?
Yeah.
And as far as the relatively crude methods we've used, we think that the exciton sits over at least 5, substantially on at least 5 molecules along the stack.
Yeah.
So that it definitely knows about the handedness of the environment it's in, but that obviously must dilute the sort of, or moderate something of what I presented. But we started with I think if I can make another sort of science point, if you look casually at these structures at high symmetry points for the electronic states, there is no chirality.
Yeah.
It's only at these off high symmetry points where the bands split.
Yeah.
And I think that might have confused some of the literature.
Oh, yeah, good point. Yeah, yeah, thanks.
Well, thank you for your questions, audience. First, a public service announcement, which is we've got a 20-minute break, and we'll be reconvening at 11:05 a.m., so please be sure to join us then. But please join me in thanking both Richard Friend and Michael Graetzel once again for kicking off a great day. Thank you, Richard and Michael.